So we're going to get started with the 2-3 lesson, okay? And I'm going here. And again, here's the learning objectives. It's not something you're memorizing, but you want to read these and make sure they make sense to you. So we're going to start with example 2. And I am on page 79, and we're just going to go over this with you on the calculator to make sure this makes sense to you. This is something that you probably did in Algebra 2, but I know it's been a while since people did this. So take 30 seconds and find your calculator, please. We're all here now. So on your calculator, you're going to follow along here. Example 2 is the greatest integer function. I go to y equals, and I do not want this. I'm going to go to math, number 5. Math, NUM 5. And if I went too fast for you, ready? You want the greatest integer function. So you can always go here. And y equals, and I can go to second 0, which is the catalog. And everything is alphabetical in the catalog. And you can't see it here, but this, well, now you can. This alpha symbol comes up automatically, which means you're in alpha mode without touching the green key. So I went greatest integer. I just push J, it takes me through everything. And I scroll up, and there it is. Okay, so if you don't remember how to find something, it's there, it's in the catalog, alphabetically. So integer function, I type X, zoom 4. And what happened? You get the step function. I got something else on. Sorry. So there's the step function. What does that mean? Well, it's rounding down to the next greatest integer. So if I go here, I am at 1, say I'm at 1.4. That makes sense? On the x-axis, my input's 1.4. The height gets rounded down to 1. Next greatest integer below my input. I'm at 1.9. It's still 1 because it rounded it down. Once I hit 2, it goes up to 2. So that's your step function. Now you can round it up. I go to y equals, and I insert second DEL. You insert a negative sign here and a negative sign in front of the variable. And that's the rounding up function. So what happened here? Here I am at 1.4 as my input, and the output got rounded up to a height of 2. So for what we're doing, it doesn't matter which one you have. They have the rounding down function, but just wanted you to be aware that you can graph these. You can round down and round up in terms of step function. So we go back here. This is the rounding down function. What are we looking for? X approaches. Got to read this subscript carefully. X approaches N. Superscript from the left. In math, N represents an integer. So as X goes to N from the left, the height will not equal as X approaches N from the right. Therefore, the limit as X approaches N does not exist. So I'm here, ready? Suppose I'm at 1.9. Here I go, 1.5, 1.7, 1.9. I'm approaching 2. Ends 2. But the limit as I get to 2 before I get there would be 1. If I'm at 2.1 or 2.5, 2.3, 2.1, that's getting rounded down to 2. When I get to 2 exactly, it's a 2. So the limit from the left doesn't equal the limit from the right. And if those two aren't equal, then we say the limit as X approaches N, no superscripts, DNE, does not exist. Okay? So that's your model. You're going to problem number 7. Give you a couple minutes and we're going to go over 7. Okay, so we go back to problem 7. Here's the picture. This should make sense to you. What happened here? The numerator is the absolute value of x. So whatever the input is, whether it's positive or negative, it has no SIGN. And the denominator is x. So when you're to the right of the y-axis, this thing's going to be positive, and it's something divided by itself. When you're to the left of the y-axis, your denominator is negative. So it's going to be a -1. That's it. Now, the book refers to this as jump discontinuity, which kind of makes sense because you're jumping from here to there at x equals 0. So what are we saying? The limit as x approaches 0 from the left does not equal the limit as x approaches 0 from the right. Therefore, the limit as x approaches 0 of y1 does not exist. Now, before we move on, I want to make a point about this, which is going to go back up again. This has discontinuity. But what's in y1 is a continuous function. And the reason that's true is the only time it has discontinuity is at a value that's not in the domain. So it's a little confusing. I don't know how you did, like usually what we say in algebra 2 is the function's continuous if you can trace it with your finger without taking your finger off the page. Okay? I can't do that here. But the caveat is for all points in the domain. And that really doesn't get stressed in algebra 2 or pre-calc. So this is continuous. And in the same way in your book, they refer to this picture, for example, 3, which is in the margin on page 81. Y equals 1 over x is continuous because you can trace this graph without leaving the paper on every point that's in the domain because x can't be equal to 0. You can't put 0 in the denominator. So for example, 3, the limit as x approaches 0 from the left is -infinity. It's going down to the floor. The limit as x approaches 0 from the right is positive infinity. And because those two don't match, we say the limit as x approaches 0 of 1 over x dne does not exist. Exploration 1. So I want you to do this. Take a moment on page 81. Just take 1 minute and read exploration 1, please, before we go over that. All right. So I'm looking at this thing and ready. I know what you want to do. you want to just put everything into your calculator right away. And you kind of have to give yourself, you have to pause for a moment and think about the problem and then anticipate what you think you're going to see on the calculator and see if that's confirmed. So before we do this, I look at that thing and it says factor the denominator, which is a good place to start. And everybody can do that because the denominator is difference of squares. Yes? That's step one. So now, how about the numerator? Well, how do I factor a cubic? Well, one thing, now ready? We're going to do this problem with and without a calculator. So with a calculator, I'm going to put just the numerator in y1. X cubed subtract 7x subtract 6. And I get this. And I can see, ready, that this cubic, the numerator only, is crossing the x-axis at -2, -1, and +3. Well, do you understand the cubic is a product of linear factors? So if I go back to y equals, I would have x plus 2. You don't need to do this, but just look up there. X plus 1 and x plus a -3. And if I push graph, I've got these lines that are crossing the x-axis at the same place the cubic is. So think about this. We're going to be about one line, the red line. Ready? -2 makes the red line equal to 0. So whatever you multiply that red line by, -2 has to make that product 0, because one of the factors would be 0. So if I go here, back to y equals, I just factored that cubic by coming up with the 3 linear equations that cross the axis at the same place. Now, that's nice, but it's an artificial problem because they happen to cross at the integers. Okay, so what if I had to do that without a calculator? So without a calculator, you could literally do long division. Well, where do I start? What do I divide by? And what you want to divide by is one of the factors in the denominator. So instead of doing long division, we're going to do synthetic division, which you may be familiar with and maybe not. Okay? Now, I already know this ahead of time. There's 2 linear factors in the denominator. So what makes them 0? 3 and -3. So I don't want to mess around. I already know what works. So I'm just going to start with the one that I know that works. Trial and error. 3. So you take the factor that makes, you take the value that makes the factor 0. So this is 3, which is for the line x take away 3. And you write the coefficients of the dividend, the numerator, right? 1, 0, because you have 0x squared, -7, -6. So if you had to do this problem without a calculator, instead of graphing it, you could do synthetic division, which is a shortcut for, synthetic, it's fake. It's a shortcut for doing long division of polynomials, but people don't really enjoy that. You bring the first term down, it's a 1, and then you multiply. 3 times 1 is 3. And then you're going to add. Right? You get a 3. Now we're adding. We're not subtracting here because we put the opposite of what makes of the factor. 3 times 3 is 9. We add, and we get a 2. 3 times 2 is 6. If this is a 0, This is telling us that 3 was a factor of the numerator. What am I left with? I'm left with 2 is my constant, 3 is your x term, 1 is your x squared term. So I can factor that with a lattice. My lattice would be, I have a quadratic here, x squared. The first term goes up here. Sorry for the penmanship. My last term goes here, and these two cells have to add up to 3x. So when you work out, you'd have x and a 2, x and a 1. Doesn't matter where you put the 1 and 2. And then when you filled in these cells, this would give you 2x and x and add up to 3x. So the issue being, it's taking you back I'm still not good with that. It's taking you back here to these factors, x plus 2, x plus 1. So here's how we got on the calculator by graphing it or by division. So there's the numerator, x plus 2, x plus 1 from the lattice, x take away 3, which I got a hint from the two factors that made the denominator 0. Then what? I'm just going to rewrite this. I'm going to group the x take away 3 as common to the numerator denominator, so I'm going to write it out here. Now what? Essentially what you did is you said, here's the picture that I have, but by multiplying by 1 in the form of x take away 3 over itself, you created a hole in the graph. See, if you were to just graph this thing, it'd look like this. But when you multiply it by 1, it doesn't change the shape. But putting this x take away 3 over itself in here creates removable discontinuity, a hole when x is 3. Now what? You can see the hole here because I went to the table and I made the delta table 1,000. So as you see from the left, these numbers are trying to get to 3.3 repeating, and from the right, they're trying to get to that. So that's the height of the hole. So I took just this part without this factor of 1, put it in y2, and said, what does 3 give me? It gives you 3.3 repeating. It gives you 10/3. So 10/3 is the height of the hole. That's removable discontinuity. Okay? So we're going to leave this up here. Now the example you're going to is the exercise you're going to is number 25. That is more user-friendly than this. But this one's worked out, you know, and it's on the PDF for you to refer to if you get to a harder problem. So we're going to give you a few minutes to go to problem 25, please. All right, now this problem is more user-friendly than the exploration. See what we have. The numerator is the difference of squares. There's the denominator. So I can rewrite this as just x take away 3, which is what? It's the line y equals x that has been moved 3 to the right or 3 down, doesn't matter, however way you want to look at it, times 1 in the form of x plus 3 over itself. So this is going to create a hole in the graph at -3. If I want to write this thing and fill in the hole, I change f and say, okay, I call it g. Here's the question. X cannot equal -3. That's not in the domain. So instead, we're going to define -3 to have value of -6. Where are we getting that from? Because if I put -3 in here, -3 plus a -3 be -6. okay? So if we just look at it on the calculator, you should anticipate what the shape's going to look like. It's a linear equation, okay? Except you're not going to find the hole in the graph. You're not going to find it, you're not going to see it, because it happens over here when x is -3. So I have to see what the height is at -3, which we said was -6. Now, you got to be careful here. You go to window. The whole point of using a Zoom 4 window is it matches up the pixels. So if I go to window, I'm just going to slide the window so that the pixels will still be perspective. So I slide everything down 3. So I know I got to see -6. Now, your window may be different. Like if you have the older calculator in Zoom 4, you go from -4.7 to 4.7, and from -3.1 to 3.1 for your Ys. This calculator is newer. It has better resolution. It has more pixels. But either way, you can still slide it. Push graph. There's the hole. Where is it? 3 to the left, down 6. So in effect, really what you did, you could fill in the hole like this. I go to y equals, right? And I just graph x take away 3, which you already have in there. If I take x take away 3, graph that. So you just covered, it traced y1 and it filled in the hole. Because the way you created this thing was you had this line x take away 3 and you multiplied it by 1 in the form of x plus 3 over itself, and that created the hole, okay? So we're not going to do example 5, or, here's example 5, just so you understand. It says, is any number one less than its cube? So it's okay, we call the number x. 1 less than x cubed, do they equal each other? So we had a negative x to both sides, and then say if anything is equal to 0. Does this cross the axis? It does. I don't care. It crossed the axis somewhere between 1 and 2. That's why I highlighted this. I don't care what the value is. Between 1 and 2, we can do second trace 0. There is a number, a real number, that is 1 less than its cube. All right, so that's not that critical. So here's what's going to happen.